I want you to try something next time you are just sitting on your couch.
Right.
Pull out your phone, open a browser, and tap a link. Like literally any link.
Like a random one, yeah.
Right. And I want you to really think about what happens in the milliseconds after your finger leaves the glass. It is this, well, completely invisible miracle that we all just take entirely for granted.
Oh, 100%. We don't even think about it.
You tap a screen and suddenly a page loads. Or, you can be streaming a high-definition video, stand up, walk out your front door, leave your home's Wi-Fi zone, drop onto a 5G cellular network, and the video doesn't even stutter.
It just keeps playing.
Exactly. Or like your online shopping cart somehow remembers that you put a pair of shoes in it 3 days ago, even if you closed the browser entirely and rebooted your phone. It feels like magic.
It really does. But, I mean, behind this incredibly seamless, kind of mundane experience is a massive 3-decade-long engineering war.
A war.
Yeah, a war. And the enemy in that war, the speed of light and, well, the physical limitations of copper wires and fiber optic cables that are literally spanning the ocean floor.
So it's a physical limitation.
It really is a war fought in the trenches of network infrastructure. Like, we tend to view the internet as this smooth, polished utility, right? Like running water or electricity.
You turn on the faucet, internet comes out.
Right, exactly. But underneath that surface, it is a wild testament to both incredible visionary foresight and, frankly, sheer desperation.
Desperation's a great word for it.
What you're experiencing when you tap that screen is the culmination of thousands of engineers trying to force computers across the globe to talk to each other, well, faster than the laws of physics naturally allow.
So to really understand how we got here, today's deep dive is going to explore the central nervous system of the internet itself. We're talking about HTTP, the Hypertext Transfer Protocol.
The absolute foundation.
Yeah, and we are going to trace its evolution. Because this is a journey from a very simple text protocol that was literally designed for physicists at CERN in the 1990s. Just to share academic documents.
Yes, basic text, yeah.
Right, all the way to a highly complex, encrypted, multiplexed powerhouse that essentially runs the entire modern world. We get into the hidden architecture, the brilliant design choices, the catastrophic performance bottlenecks, and the hilarious duct tape workarounds engineers used for a decade.
I love the duct tape era. It's so funny in hindsight. But HTTP isn't just for web browsers anymore. That is a huge misconception people have.
Oh, really? What else is using it?
It is the default language for almost everything digital now. The mobile applications on your phone, fleets of Internet of Things devices like smart thermostats, internal microservices, and massive corporate data centers, even machine learning inference services communicating with GPUs, they all speak HTTP.
So it's everywhere.
It is the lingua franca of distributed systems. If you want to understand how the modern world operates, you have to understand the mechanics of this protocol.
So let's dive into that hidden architecture. Before we can talk about how the web got so incredibly fast, we have to look at the original blueprint, right? Because the foundational rules of the web were established in 1997 with a standard called HTTP 1.1.
That's the one.
And the crazy part to me is those core rules have survived completely untouched to this day. Through all the massive revolutions in how data is physically beamed through the air, the fundamental concepts haven't changed a bit.
Yeah, there's a critical distinction we need to make right at the start here. In networking, there is a difference between the semantics of a protocol and the wire mapping of a protocol.
Okay, unpack that for me. Semantics versus wire mapping.
Sure. So the semantics are the meaning, right? What a request is trying to achieve. The wire mapping is how that request is physically transmitted as ones and zeros over a cable. The semantics of HTTP are the indestructible core. The Internet standards bodies actually separate this entirely now. There is one standard document for what HTTP means, and entirely separate standard documents for how HTTP 1.1, HTTP 2, and HTTP 3 actually carry that meaning over the network.
Let's start with those semantics then, the meaning part. The first big concept that trips people up, and I know it confused me, is this idea of resources versus representations.
Oh yeah, that's a classic stumbling block.
Right, because I know when I type a URL into a browser, I usually assume the web is sending me a specific file, like, a Word document sitting on a hard drive in a server farm somewhere.
Right, like fetching a book off a shelf.
Exactly. But that's not actually how the web works at all, is it?
No, the web doesn't send you a file. It sends you a representation of a resource.
A representation.
Yeah. The fundamental unit of interaction on the web is the resource. which is just anything you can point to with a uniform resource identifier, or URI. And a URL is just a type of URI. But you, as a client on a laptop or a phone, you never manipulate or download that raw resource directly.
Okay, so what am I actually downloading then?
Instead, you and the server exchange representations. These are sequences of bytes along with vital metadata, so things like the media type, the language, the compression encoding, and all of that captures the state of the resource at that specific fraction of a second.
Okay, let me see if I have this right. Let's use an analogy. If I use a weather app to ask for the weather in Tokyo, the resource is the abstract concept of Tokyo's current weather.
Yes, perfect.
But the representation the server sends me could take completely different forms based on who is asking.
That indirection is the absolute genius of the system. It means a single URL can serve a beautifully formatted HTML page to a human using a web browser. But that exact same URL can serve raw, unformatted JSON data to a machine querying an API.
Oh, wow. So it's context dependent.
Totally. It can serve a translated French version to a user in Paris, or a highly compressed version to a mobile phone on a really slow connection. The client and the server negotiate this representation at the time of the request using headers like accept or accept language.
So the resource itself is a constant abstract concept, but the representation is entirely flexible.
Exactly. You ask for the concept, the server gives you the flavor you can actually digest.
Which brings us to how we actually ask for these representations.
Yeah.
We use what are called methods or HTTP verbs.
Right. VT, POST, that kind of thing.
Yeah, and these aren't just stylistic choices for programmers, are they? They are incredibly rigid contracts that govern how the entire internet behaves.
They are literal contracts with the entire invisible infrastructure of the internet. Like every router, every proxy, every cache between you and the server looks at those methods.
So what are the actual properties we care about with these methods?
The three critical properties we care about are whether it is safe, whether it is idempotent, and whether it is cacheable.
Okay, let's break those down because this is where the theory hits reality for anyone who uses the internet. Let's start with safe. A safe method means it's read-only. The client is not asking the server to change anything in its database.
Right. The classic example is the GT method. When you get a web page, you are just looking at it. You aren't changing the database on the server.
I'm just reading the news. I'm not writing an article.
Exactly. And because it's safe, automated systems like Google's web crawlers can confidently prefetch and scrape these URLs by the billions without worrying about accidentally, deleting someone's account or triggering a financial transaction.
That makes total sense. Then we have idempotent. It's a fun word to say. It basically means that doing the action once has the exact same effect as doing it 100 times in a row.
That's exactly it. And all safe methods are idempotent by default. If you read a web page once or you read it 50 times, the server state remains unchanged.
Right.
But methods like putty and delete are also idempotent, even though they intentionally change state.
Wait, really? How does that work if they are changing things?
Think of it like an elevator button. If I press the button for the 4th floor, the elevator is instructed to go to the 4th floor. If I aggressively press that same button 50 times in a row because I'm in a hurry,
Which we all do.
right, the end result is exactly the same. The elevator goes to the 4th floor. The system state is identical whether it processed the command once or 50 times.
Oh, I see.
Yeah, so if I send an HTTP delete command for a specific photo, the photo is gone. If my connection drops and my browser automatically retries that same delete command 5 more times, just to be sure, it doesn't matter. The photo is still gone.
Okay, so this actually explains something I've always wondered about. If you've ever bought concert tickets online or tried to pay a utility bill on a poorly designed website, you know this specific panic.
Oh no, I know exactly where you were going with this.
You fill out your credit card info, you hit submit, the page just hangs there spinning, and you see that terrifying red text. Do not press reload or hit the back button. Your credit card may be charged twice.
The dreaded double charge warning.
Yes. Why does that happen? If the internet is so smart and has all these idempotent rules, why can't it just figure out, I only want to buy the tickets once?
That panic is the direct result of a developer using a method that is neither safe nor idempotent, and usually that method is POST.
POST.
Yeah, POST is the wild west of HTTP. It is designed to process data and change state, but it makes zero guarantees about repeatability. If you send a POST request to a server that says buy tickets, the server processes it and you buy 2 tickets. If you hit reload, you send a second identical POST request.
And it just buys them again.
Yep, the server processes it again, and you just bought 4 tickets.
And the browser actually knows it's about to do this, right?
Oh, absolutely. The browser and all the intermediaries on the network, they all know that POST is not idempotent. Therefore, if a POST request gets interrupted, say your Wi-Fi blips out right as you hit submit, the browser doesn't know if the server received the request before the connection died.
Because it didn't get the receipt back?
Right. And because it's POST, the browser is strictly forbidden by the HTTP standard from automatically retrying it behind the scenes. It cannot risk double charging you.
Oh, wow.
Only the human user can make the decision to risk a retry, which is exactly why your browser throws up that terrifying warning box when you try to refresh a page after submitting a form. The choice of method dictates how every piece of software between your phone and the data center handles your data in the event of a failure.
That is fascinating. It's not just a programming convention, it's a safety mechanism for the whole network. Okay, so we have resources, representations, and methods, but now we have to talk about what is arguably the most fundamental design choice of the entire web, and it's the massive double-edged sword, statelessness.
Statelessness, yes, this is the big one.
Explain this because it seems counterintuitive to how we use the web today.
So, statelessness is the architectural commitment that allowed the web to grow into the largest distributed system ever built by humanity. What it means is that every single HTTP request must carry all the information necessary for the server to understand it, completely in isolation.
Okay.
The protocol requires absolutely no memory on the server side of any previous requests.
I like to picture it like every time you talk to a server, the server has complete amnesia. It's like the movie 50 First Dates.
That is a brilliant analogy.
You click a link and say, "Hi, I'm user 123, here's my request." The server replies, and they could click the very next link on the exact same website, and you have to say again, "Hi, I'm user 123, here is my request." The server has zero recollection that you just spoke to it 2 seconds ago.
That amnesia is actually a superpower for scaling a business because the server doesn't have to remember who you are or, keep a dedicated memory slot open for your connection. Any server replica in the world can answer your request.
Because all the context is in the request itself.
Exactly. Think about Amazon on Black Friday. If they suddenly have millions of people logging on, they can spin up 10,000 brand new servers in the cloud. They can route your very next click to a server that didn't even exist a minute ago, and that brand new server can fulfill your request instantly.
Because it doesn't need to ask the old server what you were doing.
Right. It makes infinite horizontal scaling possible. It also makes intermediaries like content delivery networks possible, because a request's meaning doesn't depend on some hidden conversation history.
But wait. If the protocol is stateless, how do modern applications actually work? Because if I'm shopping online, the application desperately needs state. It needs to remember what's in my cart.
It absolutely does.
If I log into my bank, it needs to remember that I'm authenticated as I click around to view different accounts. So how did engineers solve this massive collision between a protocol that refuses to remember anything and applications that require constant memory?
They invented a workaround in 1994. And it changed the internet forever.
1994. Who was it?
Lou Montulli, an engineer at Netscape Communications, he was trying to build a virtual shopping mall for a client. And he ran headfirst into this exact amnesia problem. How do you build a shopping cart if the server forgets the user after every click?
Right.
He couldn't rewrite the entire HTTP protocol, so he created a mechanism to bolt state onto it. He invented the cookie.
The cookie.
Yeah.
So how does a cookie actually solve the amnesia problem mechanically? Like, what is it actually doing?
It works by forcing the client, your browser, to hold the memory instead of the server.
Ah, clever.
Yeah, so when you log in or put an item in a cart, the server generates a unique piece of data. Let's call it a session ID. It's just a long string of random characters. The server sends your browser a response with a special header called setCookie.
Okay, so it hands me the string.
It hands you the string and basically says, store this string of characters, and whatever you do, don't lose it. Then, on every single subsequent request your browser makes back to that specific domain, your browser automatically attaches a cookie header containing that exact string.
So the server's basically handing me a name tag and saying, I have no idea who you are, and I'm going to forget you instantly. Please wear this name tag and show it to me every single time you ask me for something.
Exactly.
And then the server looks at the name tag, checks its database, and says, oh yes, user 123, you have a pair of shoes in your cart.
That is exactly how it works. The heavy session state, like the actual list of items in the cart, might still live in a database on the server, But the key to unlock that state is carried by the client and presented on every single request.
But this bolted-on state mechanism accidentally created a massive surveillance monster, didn't it? Because cookies weren't just used for shopping carts and bank logins. They became the tracking foundation of the entire digital economy.
Yeah, this is where we get into the concept of third-party cookies, and it's a huge privacy issue.
Explain how that works, because it sounds shady.
So the core rule with cookies is that a browser will only send a cookie back to the domain that originally set it. If Amazon.com sets a cookie, your browser will only send it to Amazon.com, not to Google.com.
Well, that sounds secure. Like they stay in their lane.
It does sound secure until you realize how modern web pages are actually built. A web page isn't a single document. It's a collage of resources pulled from dozens of different servers.
Right. Images, scripts, ads.
Exactly. So if you visit a cooking blog, the main HTML might come from the blog server, but the blog might embed a small advertisement or even an invisible one-by-one pixel image that is hosted by a totally different company, an advertising network.
And because my browser has to make a separate HTTP request to that ad network to fetch that invisible pixel, the ad network can use the set cookie header on that response.
Yes. The ad network sets a cookie on your browser. Now, you leave the cooking blog and you go to a sports website. The sports website also happens to embed a tiny pixel from that exact same ad network.
Oh no, I see where this is going.
Yeah. Your browser makes a request to the ad network to load the pixel on the sports site, and because of the rules of the web, your browser helpfully attaches the cookie that the ad network set when you were on the cooking blog.
So the ad network server looks at the name tag and says, aha, the person who is currently looking at football scores is the exact same person who was looking at a recipe for lasagna 10 minutes ago.
Exactly. The ad network has successfully correlated your identity across two completely unrelated websites. And by embedding these trackers across millions of websites, these networks build massive, comprehensive profiles of your browsing history, your interests, your habits.
That is just wild.
It is the engine of the surveillance capitalism economy, and it all spawned from a hack designed in 1994 to make a shopping cart work on a stateless protocol.
That is just wow. And because this was a bolted-on hack, the security implications must have been an absolute nightmare.
Oh, a total nightmare.
Right, like if my browser is automatically attaching this name tag to every request, what happens if someone steals the name tag?
It's game over. If an attacker gets your session cookie, they can impersonate you perfectly. The server can't tell the difference between your browser sending the cookie and an attacker's browser sending the cookie. This vulnerability led to a decades-long game of whack-a-mole, patching the cookie specification to fix security holes.
Give me an example of how an attacker would actually steal it and how they patched it.
They introduced a patch called the HTTO only attribute. When the server sets the cookie, it can add a flag saying HTTP only. This tells the browser, you can attach this to HTTP requests, but you must absolutely forbid any JavaScript running on the page from reading it.
So it walled off the cookie from the programming environment.
Exactly. It made the cookie invisible to JavaScript.
Okay, that stops the theft. But wasn't there another way to abuse cookies without even stealing them?
Yes, a much more insidious attack called cross-site request forgery, or CSRF, and this exploits the very nature of how browsers helpfully attach cookies automatically.
How does that work?
Let's say you are logged into your bank in one tab. In another tab, you click a link to an attacker's website. The attacker's website contains a hidden form that is programmed to automatically submit a POST request to your bank's URL for transferring money.
Wait, so the attacker's site triggers a request to my bank?
Yes. And because your browser sees a request going to the bank's domain, it helpfully automatically attaches your bank session cookie to that request.
Oh my God.
The bank receives the request, sees your valid cookie, assumes you authorized it, and transfers the money. The attacker never stole your cookie, they just tricked your browser into using it.
That is terrifying. It's like the confused deputy problem. The browser is too helpful for its own good. So how did they patch that one?
It took years, but they finally introduced the same site attribute. This allows a server to tell the browser, only attach this cookie if the user is actually actively navigating on my site. If the request is being triggered by some other website in a different tab, do not send the cookie.
It's fascinating how much duct tape is holding the internet's security model together. It's just patch upon patch.
It really is.
Okay, so this brings us to the next massive challenge. Because the web is stateless, as we just discussed, every single request has to fetch what it needs from scratch. But if we actually did that every time, if your browser downloaded the massive Amazon logo every single time you clicked a new product, the internet would grind to a halt, right?
Instantly. The bandwidth costs would bankrupt companies, and the latency would make the web completely unusable.
So how does it survive?
This is where caching comes in. Caching is HTTP's oldest, most effective, and most critical performance optimization. Storing responses locally, whether that's inside your browser's memory, at a proxy server sitting in your office's IT closet, or at a massive content delivery network edge server sitting in a data center in your city, is the infrastructure consequence of the statelessness we just talked about.
Okay, so how does my browser actually know when it's safe to use a saved copy of an image and when it needs to go back to the server to get a new one? You can't just guess.
No, it relies on very specific HTTP headers. There are two distinct branches of caching mechanics: freshness and validation. Let's start with freshness, which is really the holy grail of web performance.
Freshness. Okay, hit me.
When the origin server sends a file, say a logo, it includes a header called cache control. This header declares a freshness lifetime. It might say max age 3600. This tells your browser this asset is guaranteed not to change for 3600 seconds or 1 hour.
Okay, so it starts a timer.
Right. Your browser saves the file and starts a stopwatch. For the next hour, anytime you navigate to a page that needs that logo, your browser doesn't even talk to the network. It intercepts the request internally and serves the file directly from your hard drive.
That means zero network latency. It's instantaneous.
Instantaneous. But it is a deliberate trade-off. It is a consistency trade. During that 1 hour fresh window, if the marketing team at the origin server decides to update the logo, the server has no way to push that update to you.
Because it's stateless, it doesn't know who has the old logo.
Exactly. Your browser isn't asking. You will continue to see the old, stale logo until your stopwatch hits 3600 seconds. The engineers running the origin server are buying massive offload and lower latency by accepting bounded staleness. It's a time-to-live-based eventual consistency scheme.
Right. I promise this logo won't change for an hour, so don't even bother asking me. But what happens at second 3601? Does the cache just throw the file away and download the whole massive image again?
No, and this is where validation comes in, the second branch. When a response becomes stale, meaning the stopwatch ran out, the cache doesn't have to blindly refetch it. It can attempt to revalidate it using a conditional request.
How does that work?
When the server originally sent the file, it likely included a validator. This is a piece of metadata like an entity tag or e-tag. An e-tag is usually just a cryptographic hash of the file's contents. Let's say the e-tag is version 42, or the server might send a last modified timestamp.
So my browser still has the file, but it's expired. So it knocks on the server's door and says, hey, I have this file, and its e-tag is version 42. Has this changed since version 42?
Exactly. The browser uses a conditional header called ifNoneMatch.version42. The origin server receives this tiny request, checks its database, and calculates the e-tag of the current file. If the file hasn't changed, the e-tag is still version 42. So instead of sending the entire 5 megabyte image back over the network, the server performs a little bit of magic.
What's the magic?
It responds with a special status code, 304, not modified.
304, not modified. What does that actually look like on the wire?
It is a response that includes headers, telling the browser to reset its stopwatch for another hour. But it includes absolutely no body, no data payload. It is just a tiny little ping saying, nope, you're good. Keep using the one you have.
That is brilliant.
It is a massive optimization. A 304 response costs 1 round trip of latency, but virtually 0 bandwidth. If you have a massive video file or a huge JavaScript bundle on a slow 3G connection, that 304 response converts what would have been a 10-second download into a single network round trip, maybe 50 milliseconds.
And there's a mathematical reality here about why caching is the entire backbone of web performance. It's the expected latency identity. Explain how the math proves that caching is the only thing that really matters.
Okay, so the formula for expected latency in any system is simple. It is the hit ratio multiplied by the latency of a cache hit, plus the miss ratio multiplied by the latency of a cache miss.
Okay, basic algebra.
Right, but the structure of that formula is where the real lesson lies. The time it takes for a cache miss going all the way back across the country to the origin server, querying the database, generating the HTML, and sending it back is astronomically larger than the time it takes for a cache hit locally or at a CDN edge server in your neighborhood.
We are talking hundreds of milliseconds versus 1 millisecond.
Exactly. So because the mislatency is so huge, it completely dominates the entire equation.
So making a cache hit faster doesn't even matter.
Not really, no. Shaving a few microseconds off the cache hit time doesn't move the needle at all. All that matters is raising the hit ratio, turning misses into hits. If you look at a graph of page load times for any major website, the tail of the latency distribution, those painfully slow page loads that make users abandon their shopping carts, is entirely a story about cache misses. That is why every single layer of modern web infrastructure, your browser cache, the intermediate ISP caches, the massive global CDN edge networks, they're all just massive, multi-billion-dollar financial investments in raising that hit ratio by fractions of a percent.
Okay, so that's how we create the illusion of speed via caching. Let's talk about how we create the illusion of safety. HTTPS, HTTP carried inside a TLS or transport layer security cryptographic channel.
The famous padlock.
Right. Almost all web traffic today is HTTPS, and since the late 90s, everyone has been taught one cardinal rule of internet safety. Look for the padlock icon in the browser address bar to know a site is secure and legitimate.
And we need to completely dismantle that myth right now.
Ooh, okay.
Go. The padlock icon represents a very specific mathematical cryptographic contract, but it does not mean what the general public thinks it means. TLS provides 3, and only 3, guarantees for the bytes in transit over the wire.
Okay, lay them out. What are the 3 guarantees?
Guarantee number 1 is confidentiality. No observer sitting on the network path between your device and the server can read the contents of your request or response. Your internet service provider, the hacker at the coffee shop, the government tapping the undersea cable, none of them can read the URLs you are visiting, the headers, the cookies, or the body of the message.
Though it's worth noting, they can still see some metadata, right? Encrypted doesn't mean you're a ghost.
Correct. It's not perfectly private. An observer can see the destination IP address you are connecting to, they can see the timing of the packets, and they can see the sheer volume of traffic.
So if I connect to a hospital's IP and download a huge file.
Right. If you download a 500 megabyte file, they know you are interacting with the hospital, even if they can't see what the file actually is, but the payload itself is confidential.
Okay, what's guarantee number 2?
Guarantee number 2 is integrity. No party on the path can modify, reorder, or inject content into the stream without the cryptographic math failing and the connection immediately terminating.
Which is huge, because before HTTPS was everywhere, it was super common for shady ISPs or public Wi-Fi networks to literally inject their own advertisements into the web pages you were downloading. So integrity mathematically prevents tampering.
Exactly. And guarantee number 3 is server authentication. The client knows, via cryptographic proof, that it is speaking to the holder of the private key for a certificate that binds the server's domain name to a public key.
So it proves they own the domain.
Right. Your browser checks a chain of trust, verifying cryptographic signatures all the way up to a root certificate authority pre-installed on your computer to ensure the certificate is valid, unexpired, and matches the domain you requested.
Okay. Confidentiality, integrity, and server authentication. That sounds incredibly robust. Why did you say we need to dismantle the myth of the padlock?
Because of what the contract explicitly excludes. The padlock authenticates the endpoint, but it says absolutely nothing about the honesty, legality, or security practices of the organization running that endpoint. And this has become a massive problem because of how easy it is to get certificates today.
Right. With services like Let's Encrypt, anyone can get a certificate for free in seconds.
Yes. Let's Encrypt is wonderful because it encrypted the web, but it only validates domain control. If an attacker registers a typo squatting domain, let's say they register paypay1-secure-login.com with a number 1 instead of an L, they can easily prove they own that fake domain, and they will receive a perfectly valid TLS certificate.
Oh, wow.
So when a victim clicks a phishing link and goes to that fake site, the padlock will appear in the browser. The connection will be confidential, it will have integrity, and it will be authentically connected to the attacker's server. The padlock does not mean this is a legitimate business.
That's a terrifying reality check.
Yeah.
The padlock just means you are securely communicating with a scammer. No one can eavesdrop on you handing your password to the hacker.
Exactly. You have a completely secure pipe to a criminal. Furthermore, the padlock says nothing about what happens to your data after it's decrypted at the endpoint. And here is the real structural secret regarding modern web architecture. The secure connection is almost never terminated by the actual company you think you are talking to.
Wait, what?
It is usually terminated by a middleman.
Wait, how does that work? If the encryption is end-to-end, how can a middleman be involved?
Because the internet relies on content delivery networks, CDNs like Cloudflare or Fastly, for performance and DDoS protection. When you connect to a major e-commerce site, your TCP connection doesn't go to their headquarters. It goes to a CDN edge server located a few miles from your house. But for the CDN to cache the traffic or block malicious requests, it has to be able to see the unencrypted HTTP data.
But the TLS certificate is bound to the e-commerce site's domain. How does the CDN decrypt it?
The e-commerce company literally delegates or hands over their private cryptographic keys to the CDN.
You kidding?
Nope. The CDN edge server acts as an authorized impersonator. It terminates the TLS connection, decrypts your traffic, inspects it, logs it, caches it, and then opens a brand new separate encrypted connection from the edge server back to the origin server.
Wow. So the secure channel has fully authorized built-in man-in-the-middle decryption by design. The end-to-end encryption only goes as far as the edge of the network, and you are putting massive, implicit trust in the CDN's internal security, not to leak your passwords or credit card numbers while they sit in plain text in the CDN's memory.
Exactly. It's necessary for performance, but it totally changes the threat model.
Okay, we've covered the indestructible core semantics, the massive hack of cookies, and the realities of caching and encryption. But now we have to get into the real drama.
The physical limitations of the network.
Yes. We have to transport ourselves back to the early 2000s. The web was evolving rapidly. Websites stopped being simple text documents. They became massive applications. Suddenly, a web page wasn't just an HTML file. It was an HTML file that referenced 100 small assets, images, JavaScript files, CSS style sheets.
And HTTP 1.1, riding on top of the TCP transport protocol, fundamentally broke under this weight.
It just couldn't handle it.
It broke because of a collision between the protocol's design and the physics of the network. HTTP 1.1 was brutally simple. It was text-based. You opened a connection, sent one text request, and waited for the complete response to come back in order. That simplicity was its undoing for complex pages.
So what were the actual costs that made it break?
The problem decomposes into three interacting costs, starting with the setup tax.
The setup tax. Explain this, because it is the reason why upgrading your home internet from 100 megabits to a gigabit fiber connection doesn't actually make a standard web page load 10 times faster.
Right. It comes down to round trips and the strict limitations of the speed of light. Every time your browser needs to open a new connection to a server to download an asset, it has to pay a massive setup tax before a single byte of actual HTTP content is transferred.
What's the tax made of?
First, it has to do a DNS lookup to find the IP address of the domain, like looking up a name in a phone book. That takes time. Then it has to perform the TCP handshake. TCP requires a three-way handshake, SYN, SYN, ACK, ACK. That takes one full round-trip time, or RTT, across the network. Then it has to perform the TLS cryptographic handshake, which in older versions took 2 full RTTs just to negotiate the cipher suites and exchange keys.
Let's put real numbers to that. If the server's across the country, say in Virginia, and you are in California, one round trip might take 80 milliseconds.
Yeah.
So you were spending 240 milliseconds just saying, hello, are you there? Can we talk securely?
Right.
Before you even ask for the web page.
Exactly. A quarter of a second is gone just establishing the channel. And then it gets significantly worse because of a mechanism built deeply into TCP called slow start.
Slow start. Why does TCP have a slow start? That sounds like a terrible feature for speed.
Because TCP is a fundamentally conservative, polite protocol. It was designed in an era where the internet could easily suffer from congestion collapse. TCP doesn't know how much bandwidth is available on the path between you and the server. It doesn't want to flood the network with massive amounts of data, overload a router, and cause packets to drop.
Okay, so it plays it safe.
Very safe. So it starts by sending a very tiny amount of data in its initial congestion window. Historically, this was just 1 or 2 packets, but today it's usually around 14 kilobytes.
14 kilobytes. That is nothing. That's a fraction of a small image.
It is nothing. The server sends 14 kilobytes and then completely stops. It waits for your browser to send an acknowledgement back saying, I got it. That takes another full round trip. Once the server gets the acknowledgement, it doubles the window to 28 kilobytes. It sends that, stops, and waits for another acknowledgement. Then 56 kilobytes.
So it tiptoes into the pool, it doubles its speed every round trip.
Right. But here is the critical flaw for web performance. Modern web assets, a small script, a CSS file, an icon, are usually only a few tens of kilobytes in total. Therefore, the entire file transfer is often finished while TCP is still tiptoeing, still in its slow start phase.
Oh.
It never gets the chance to open the window wide enough to utilize your gigabit internet connection. Therefore, the transfer is entirely bottlenecked by the latency of those round trips, not the overall bandwidth capacity of the pipe.
Wow, so bandwidth doesn't even matter for small files.
Not at all. Delivering a 300 kilobyte response on a fresh connection might cost 4 or 5 round trips. It doesn't matter if you have a dial-up modem or a fiber optic cable, the speed of light dictates that the file takes half a second to arrive.
This means network connections are incredibly valuable capital assets.
Yeah.
Like a warm connection that has already paid the setup tax, done the handshake, and grown its congestion window is precious.
Extremely precious.
This is why HTTP 1.1 introduced persistent connections, right? The keep alive header, allowing the browser to reuse the same connection for multiple requests.
Yes, that helped a lot.
But even with persistent connections, HTTP 1.1 suffered from a core villain that brought the web to its knees: head-of-line blocking. Let's use an analogy here.
I love analogies. Go for it.
Imagine HTTP 1.1 over a single TCP connection is like a single checkout lane at a grocery store. The rule is strict first in, first out. If the person at the front of the line is paying for a massive cart of groceries entirely in pennies, which in our world is a massive slow-to-generate HTML file or a huge video, everyone else in line behind them is completely blocked.
Stuck waiting.
Right. It doesn't matter if the person right behind them just has one pack of gum ready with exact change, which would be a tiny CSS file that is already cached in the server's memory and ready to blast down the pipe. The gum buyer has to stand there and wait until the pennies guy is completely finished.
That is a perfect visualization of head-of-line blocking. In HTTP 1.1, responses had to be returned strictly in the order they were requested. There was no way to interleave the data. If you asked for the HTML, then a CSS file, then an image, the server was mathematically forced to send the HTML completely before it could send the first byte of the CSS.
Even if the CSS was ready.
Exactly. If the HTML required a complex database query that took 2 seconds to generate on the server, the TCP connection sat completely idle for 2 seconds. Those other assets were blocked at the head of the line, even if they were ready to go.
And there was a proposed fix for this in the protocol, wasn't there? HTTP pipelining.
There was. Pipelining allowed the client to send all its requests at once without waiting for the responses, like give me A, B, and C. But it didn't fix the core architectural issue. The server still had to send the responses back strictly in the order of A, B, C.
Why couldn't they mix it up?
Because the protocol was just a stream of plain text. There was no mechanism to identify which bytes belonged to which file if you mixed them up. If the server sent a chunk of A, then a chunk of B, the browser would have no idea how to reassemble them. It was just a continuous river of text.
And worse, I read that the middle boxes on the internet, like the corporate firewalls and cheap home routers, handled pipelining so poorly that it caused massive connection failures, and browser vendors eventually just gave up and disabled it.
It's a classic case of protocol ossification. The infrastructure of the internet becomes so rigid that it refuses to let new features work. Routers expect traffic to look exactly like it did in 1999, and if it doesn't, they drop the packets.
So, faced with this crippling bottleneck, the setup tax making new connections slow, and head-of-line blocking making single connections inefficient, web developers essentially lost their minds. They entered an era of desperate duct tape engineering. If one connection was blocked by a slow file, what did they do?
They brute forced it.
They just opened more connections.
Yes. Browsers started allowing up to 6 parallel TCP connections per host domain. But developers building complex web apps needed way more than 6 concurrent downloads. So they invented a hack called domain sharding.
Domain sharding?
They would take their hundreds of images and intentionally spread them across fake subdomains. So mng1.example.com, img2.example.com, img3.example.com. All of these domains pointed to the exact same physical server, but to the browser, they looked like different hosts.
So the browser says, oh, a new host. I can open 6 more connections to this one. And suddenly you have 24 or 30 parallel TCP connections all firing at once.
It was a brute force assault on the network. The costs were massive.
Yeah.
Every single one of those parallel connections had to pay its own DNS, TCP, and TLS setup tax. Every single one had to go through TCP slow start simultaneously. They competed with each other for the user's limited bandwidth.
It's just chaos.
And worse, they defeated TCP's built-in congestion control, making the network behave highly aggressively, which caused packet loss for everyone else on the network.
And the hacking didn't stop at the network layer. Developers started doing deeply unnatural things to the files themselves to get around the limits. Spriting. I remember having to do this.
Oh, image spriting. What a time to be alive.
You would take 50 different icons for a website, the home button, the login button, the shopping cart, and instead of having 50 image files, you would glue them all together into one massive single image file in Photoshop. Then you would write complex CSS to selectively show just a tiny 20-pixel window of that massive image for the different buttons.
Image spriting and its cousin, file concatenation. Developers would take 20 different JavaScript files representing different parts of their application and use a build tool to bundle them into one massive multi-megabyte monolith file. Why? Because downloading one massive file avoided the setup tax of 20 separate connections.
But from a caching perspective, this is a disaster.
It was a tragedy. It defeated the granularity of caching entirely. If you have a 2-megabyte concatenated JavaScript bundle and a developer changes a single line of code in one small helper function, the e-tag changes. You now have to invalidate the entire 2-megabyte bundle for every single user on the internet.
So you re-download the whole 2 megs just for one line of code.
Exactly. You lose all caching efficiency.
Yeah.
Applications were contorting their actual code bases in bizarre, unmaintainable ways simply to accommodate the physical limitations of the network transport layer. It was clear the industry could not continue down this path.
Which brings us to the first great revolution. After nearly 2 decades of this duct tape engineering, the tech giants decided enough was enough. Google, having massive control over both a dominant browser in Chrome and dominant servers in search and YouTube, unilaterally created an experimental protocol called SPDY.
SPDY.
They proved it worked, and that forced the internet standards bodies to act. In 2015, HTTP2 was standardized and released to the world to kill the workarounds.
The mandate for HTTP2 was strict. You cannot break the web. The semantics must remain identical. Methods, headers, status codes, URLs, they all stay exactly the same. But the underlying wire mapping, how the data is formatted, was completely ripped out and replaced. The plain text format of HTTP 1.1 was thrown in the trash. HTTP 2 introduced a binary framing layer.
The binary revolution. What does it actually mean to move from text to binary frames?
In HTTP 1.1, a request was just a continuous stream of ASCII characters, like getIndex.html followed by headers followed by a blank line. In HTTP 2, every piece of data is chopped up into explicit, structured binary frames. There is a headers frame, a data frame, a settings frame, and crucially, every single frame is tagged with a stream identifier. A stream is just a logical connection representing one request-response pair.
And this tagging allowed for the magic word of HTTP2, multiplexing.
Exactly. Because every frame on the wire is labeled with its stream ID, frames from dozens of different streams can be interleaved freely on a single TCP connection.
Let's go back to our grocery store analogy. Instead of a single checkout lane where the Finny guy blocks everyone, HTTP2 replaces the lane with one massive high-speed conveyor belt.
I like this.
Your groceries, the HTML, my groceries, the CSS, and someone else's groceries, the images are all chopped up into little labeled boxes. Those boxes are thrown onto the conveyor belt in whatever order they are ready. A box of HTML, the box of CSS, another box of HTML. They all flow down the single belt, and the cashier, the browser at the other end, sorts them all out perfectly based on the barcode on the box.
Because of the stream IDs.
Right. So the slow HTML file no longer blocks the images. They all trickle through together concurrently over one single connection.
That is the essence of multiplexing. One warm, fully ramped up, persistent TCP connection per origin domain replaces the 30 connections and the domain sharding. The congestion window stays large, the handshakes are paid only once, and head-of-line blocking at the application level is completely eliminated.
That sounds like a complete victory.
Yeah.
But this multiplexing exposed a brand new problem, didn't it? If you are sending hundreds of concurrent requests over one connection, you're suddenly sending the exact same massive HTTP headers over and over again.
Oh, the header bloat.
Every request has the user agent string, the accept headers, and most importantly, those massive multi-kilobyte tracking cookies we talked about earlier. Sending all that text repeatedly over one connection was incredibly redundant. They needed to compress the headers.
And here we enter one of the most fascinating security deep dives in internet history. When the engineers realized they needed to compress the headers, the obvious solution was to just use standard gzip or deflate compression, the same algorithms we use to compress HTML bodies. But they couldn't.
Why not?
Because compression and confidentiality are fundamentally in mathematical conflict.
Wait, pause. How can making a file smaller make the encryption less secure? The encryption happens after the compression, right? So the attacker just sees a smaller blob of encrypted garbage. How does that help them?
It's a side-channel attack, and it relies on understanding how compression algorithms like LZ77 actually work.
Okay, tell me how they work.
Compression algorithms look for repeated strings of text in a file. When they find a repeat, they replace the second instance with a tiny pointer back to the first instance. This makes the file smaller.
Makes sense.
Now imagine an attacker sitting on your Wi-Fi network. They want to steal your secret session cookie, which is, say, 20 random characters long. The attacker uses malicious JavaScript loaded in another tab to force your browser to constantly make requests to your bank. Critically, the attacker can control part of the data in those requests, like the URL path.
Okay, so the outgoing request contains the attacker's injected text in the URL, A&D my secret cookie, sitting down in the headers.
Right. And then the entire header block is compressed together before being encrypted. The attacker cannot read the encrypted output, but they can observe the exact size and bytes of the encrypted packet as it flies over the Wi-Fi.
Okay, so they are watching the file size.
So the attacker plays a game of mastermind. They start guessing your cookie one character at a time. They inject a guess into the URL, cookie A. The compression algorithm runs. Because cookie A does not match the actual secret cookie, there is no repeated pattern. The compressed size stays relatively large. The attacker observes this.
Right.
Then the attacker guesses cookie S. They happen to guess the first letter of your actual secret cookie correctly. The compression algorithm sees cookie S in the URL, and it sees cookie S in your actual header. It recognizes a repeated pattern. It compresses them together. The total size of the final encrypted output shrinks by a few bytes.
Oh my God. The attacker doesn't need to break the encryption at all. Just by watching the size of the encrypted packet get slightly smaller, the network itself leaks the fact that they guessed the letter correctly. Then they guess the second letter, watch the size shrink again, and just brute force the entire cookie in a matter of seconds.
Yes. This is a devastating known class of attacks called crime. Compression ratio info leak made easy.
Crime. It is so clever and so scary.
The compressed length becomes an oracle, a side channel leaking the plain text secret. Because of this vulnerability, HTTP2 could not use standard string compression on headers. The engineers had to invent an entirely new, bespoke header compression scheme from scratch called HPS.
HPACK. So how does HPP compress things without falling victim to the crime attack?
HPACK avoids compressing arbitrary strings across different fields. Instead, it relies on shared state lookup tables between the client and the server. It has a static table pre-populated with common headers like GAT or 200OK, but more importantly, it has a dynamic table that remembers the headers sent on this specific connection.
So it remembers the past.
Right. So the first time your browser sends that massive tracking cookie, it sends it in full text. HPACK stores it in, let's say, slot 62 of the dynamic table. The next time you make a request, instead of sending the massive cookie string again, HPACK simply sends a tiny 1-byte index pointing to slot 62. The server looks at slot 62 and reconstructs the header. It achieved 85 to 90% compression without ever exposing the crime string matching vulnerability. It is a masterclass in secure protocol design.
Wow. So HTTP2 was a triumph. It fixed the head of line blocking with binary multiplexing. It fixed the header bloat safely with HP. It sounds like the perfect protocol. But there was a tragic flaw, a fatal flaw that no one fully appreciated until the protocol was deployed at scale across the real messy internet.
Yeah, it was a heartbreaking realization for the networking community. HTTP2 successfully eliminated head-of-line blocking at the application level, but in doing so, it exposed the exact same phenomenon one layer deeper down the stack at the network transport layer.
The TCP head of line blocking. Explain how the network layer betrayed the application layer here.
Remember the fundamental contract of TCP. TCP presents a single, strictly ordered, reliable stream of bytes to the application. TCP doesn't know what HTTP2 streams are. It doesn't know about binary frames or multiplexing. It just sees a numbered sequence of bytes. Byte 1, byte 2, byte 3.
It's just a dumb pipe.
Right. Now imagine you are on a spotty cellular network or a crowded conference Wi-Fi. Packet loss happens constantly. A packet containing bytes 400 to 500 gets dropped by a router due to interference.
Okay, the packet is gone.
In HTTP2, all of your multiplex streams are traveling inside that single TCP connection. If that one packet drops, TCP's strict ordering rule kicks in. TCP receives byte 501, 502, 503, but it realizes byte 400 is missing.
Yeah.
TCP is mathematically obligated to withhold all subsequent bytes from the browser until it asks the server to retransmit the missing packet, and that retransmitted packet successfully arrives.
So if one packet containing a tiny piece of a background image drops in the air, TCP freezes the entire pipeline.
Yes. Even though the packet sitting perfectly formed in the operating system's receive buffer might belong to entirely unrelated HTTP2 streams, like the crucial CSS file needed to render the page, or the JSON data needed to display the text, TCP won't let the browser see them. It is waiting on that one lost packet to maintain the perfect numerical sequence. One lost packet freezes every single multiplex stream on the connection for at least one full round trip, sometimes much longer.
This is the tragic irony. In the bad old days of HTTP 1.1, if you used the duct tape workaround of 6 parallel connections and a packet dropped on connection number 2, only that one specific file stalled. The other 5 connections kept downloading perfectly fine.
Yes, the workaround actually had better resilience.
But with HTTP2, because we elegantly consolidated everything into one single super connection, a single dropped packet stalls the entire web page.
Global telemetry and measurement confirm this painful reality. On clean, fast, wired networks with zero packet loss, HTTP2 was a clear performance winner. But on lossy networks like a mobile phone and a moving car with roughly 2% packet loss, the fancy, highly engineered HTTP2 was actually measurably slower than the ugly HTTP 1.1 duct tape workarounds. The bottleneck hadn't been eliminated. The engineers had just accidentally moved it down a layer from the application to the transport.
Which leads us directly into the modern era, the bleeding edge. To fix this fatal TCP flaw, engineers realized they couldn't just tweak TCP. TCP is baked into the silicon of every router, firewall, and middle box on the planet. If you change the TCP header, the routers drop the packets, it's ossified. So they had to do the unthinkable. They had to rip out TCP entirely, a foundation of the internet since the 1970s, and replace it.
This is a monumental shift in internet architecture. In 2022, HTTP 3 rolled out, and it runs on an entirely new transport protocol called QUIC. And because they couldn't invent a new protocol from scratch without those rigid middle boxes blocking it, they had to pull a Trojan horse maneuver. They built QUIC on top of UDP.
UDP, User Datagram Protocol, the wild, ruleless protocol usually used for video games, DNS, or live video where you don't care if a few frames drop.
Exactly. UDP is bare bones. It just slaps an IP address and a port on a packet, fires it into the network, and hopes for the best. There is no connection setup, no guaranteed delivery, no strict ordering, no congestion control. QUIC takes UDP as a raw conduit, and in the application space, it builds all the good necessary parts of TCP, congestion control, reliability, cryptography back into it, but it fixes the structural flaws.
So how does building it on UDP fix the head-of-line blocking?
QUIC makes the concept of independent streams native to the transport layer itself. QUIC understands that the data it is carrying belongs to different logical buckets. Therefore, if a packet drops belonging to stream A, let's say, an image QUIC only stalls stream A while it asks for a retransmission.
Because it knows they are separate.
Right. It looks at the other incoming UDP packets, sees they belong to stream B, the CSS, and stream C, the HTML, and it passes them directly up to the browser immediately. Transport head-of-line blocking is dead by construction.
That is massive for mobile performance. But QUIC didn't stop at fixing the blocking. It also went after the setup tax we talked about earlier.
It did. QUIC fundamentally rethinks how connections are established. It takes the transport handshake, which was TCP, and the cryptographic handshake, TLS 1.3, and fuses them together. Instead of taking multiple round trips to establish a connection and then secure it sequentially, QUIC does both simultaneously. A brand new connection to a server takes exactly one round trip to reach the first byte of actual data.
Ludicrous speed. But the most mind-bending feature is a zero-RTT mode, right?
Yeah.
Zero round-trip time. How is it physically possible to send data over a network in zero time?
It's not zero time. It's zero round trips before sending the payload. It relies on the magic of cryptographic resumption. If you have visited a server recently during that previous visit, the server handed your browser a secret cryptographic token called a session ticket.
Okay, I have a ticket.
Right. When you return to that site the next day in QUIC 0RTT, you don't send a hello and wait for a response. You take that session ticket, use it to encrypt your HTTP request, and send it in the very first flight of packets. You are essentially walking up to the server and instantly handing them a sealed envelope with your request inside without even waiting for them to say hello back.
Wait, hold on. If I hand the server a 0RTT packet the second I connect. What's stopping a hacker on my coffee shop Wi-Fi from just intercepting that exact packet? They can't read it because it's encrypted, sure, but what stops them from just blasting that same encrypted packet at the server 100 times?
You've hit on the exact terrifying security vulnerability of 0RTT. Replay attacks. An attacker can absolutely capture that packet and replay it. The server decrypts it using the session ticket, sees a valid request, and processes it.
And if that packet was a POST request to transfer $100 out of my bank account?
The server would process it 100 times. You'd be drained of $10,000. This is a fundamental cryptographic problem. Because the packet is sent before the server can inject fresh random entropy and nonce into the connection to prove it's a unique session, replay attacks are impossible to perfectly prevent at the transport layer.
Oh, wow. So what do we do?
This is why the QUIC protocol has a strict absolute rule. 0RTT data is strictly limited to idempotent requests.
Boom. It ties right back to our very first topic, the semantics from 1997 saving the day in the 2020s.
Precisely. The standards body realized they couldn't fix the replay attack at the crypto layer, so they leaned on the semantic layer. Because HTTP GET requests are defined as safe and idempotent, a replay attack is practically harmless. Oh no, the attacker forced the server to send me the front page of the New York Times 100 times, no financial harm done.
Right.
The semantic properties of the application layer idempotency suddenly became a structural load-bearing safety requirement at the cutting-edge transport layer. If a developer uses a POST request for a data fetch, they forfeit the 0RTT speed boost.
That is such an elegant full-circle connection. There's one more mind-blowing feature of QUIC I want to cover.
Yeah.
Connection migration. This is the feature that makes switching from Wi-Fi to cellular seamless.
Yes. Under TCP, a connection is mathematically identified by a four-tuple: your source IP address, the destination IP address, your source port, and the destination port. If any of those four variables change, the TCP connection is instantly invalidated and dies.
So when I leave my house?
When you walk out of your house and your phone switches from your home Wi-Fi router to the local 5G cell tower, your ISP gives your phone a brand new IP address. Every single active TCP connection on your phone is instantly severed. Your downloads fail, your video buffers, your game disconnects, and your apps have to frantically negotiate brand new handshakes.
A connection funeral.
Exactly. But QUIC breaks this paradigm entirely. QUIC connections are not identified by the fragile IP address. They are identified by a unique connection ID, a cryptographic token established during the handshake.
So they have a name tag now.
Right. So when your phone switches to 5G and gets a new IP address, the QUIC protocol doesn't panic. It just sends its next packet to the server from the new IP address, but it stamps the packet with the same connection ID. It basically says, hey, I'm still connection ID 1234. I just moved. Keep sending data.
That is genius.
The server's routing table updates instantly. The connection does not drop. The transition is mathematically seamless at the transport layer.
It's incredible. HTTP3 essentially looked at everything the modern mobile web desperately needed: independent streams, instant encrypted connections, and seamless physical mobility, and promoted all of those features directly into the foundational transport layer. Okay, we have traced the evolution of how the browser talks to the server, from text files to multiplexed UDP streams. But the web isn't just browsers anymore. If I'm building a mobile app, or my servers are just talking to each other in a data center, are they using this exact same architecture? Because the programmatic web machines talking to machines has undergone its own massive revolution. How do we build APIs that take advantage of all this infrastructure?
Yeah, the choice of API architecture today is essentially an exercise in matching the shape of your software's interaction to the underlying mechanics of HTTP. We have a matrix of choices, and the unifying test for all of them is: how much of HTTP's native infrastructure do you want to leverage for free, and how much are you willing to throw away and rebuild yourself?
Let's start with the classic. REST, representational state transfer. This is what most people learn first.
REST is the architecture distilled from the web itself. It maps perfectly to HTTP semantics. You use GET for reading data, POST for creating data, PUT for updating, DELETE for removing. Because it aligns so perfectly with the 1997 blueprint, a REST API inherits all of the web's infrastructure for free.
Like the caching.
Right. Your GET requests are automatically cacheable by every CDN on the path. Your idempotent PUT requests can be safely retried by any proxy if the network blips.
It's the path of least resistance. You're swimming with the current of the protocol. But REST has a massive weakness for modern applications, right? The problem of chattiness and overfetching.
Yes. Think about a mobile app like Twitter or Instagram. If the app needs to load a user profile, their recent posts, and their follower count in strict REST, that might require 3 separate HTTP GET to requests to 3 different resource URLs.
3 separate trips.
Right, like users 123, users 123 posts, users 123 followers, that's 3 round trips on the network. For a mobile device on a slow 3G network in a developing country, that chattiness is a performance killer. Furthermore, it suffers from overfetching. The user's 123 endpoint might return a massive JSON object with the user's bio, email, address, and preferences, even if the mobile app only needed to display their avatar image. You are wasting precious mobile bandwidth downloading data you immediately throw away.
So, to solve the chattiness and the overfetching on mobile, Facebook introduced GraphQL.
GraphQL is the architectural inverse of REST. Instead of making many small requests to different URLs, the client sends one massive query to a single endpoint, usually GraphQL. The client declares the exact shape of the data it wants using a specialized query language, like, I want the user's name, the first 3 posts, and just the integer count of their followers.
Very specific.
The server dynamically resolves all of that data from various backend databases, stitches it together, and returns exactly that shape in one single round trip. No chattiness, no overfetching.
That sounds vastly superior for mobile performance. It solves the exact problem. But what's the infrastructure catch? You mentioned throwing things away.
The catch is the heavy price you pay in network infrastructure. Because GraphQL queries are complex, dynamic, and can easily exceed the length limits of a standard URL, nearly all GraphQL traffic is sent via HTTP POST requests, placing the query in the body of the request.
Oh. And as we established an hour ago, POST is definitively not cacheable by default.
Exactly. When you switch your architecture to GraphQL, you throw away all of the web's native caching infrastructure. Every CDN, every intermediate proxy on the path just sees an opaque, uncacheable POS blob that cannot help you. They are reduced to dumb pipes that must forward every single request all the way to the origin server.
So you have to rebuild it yourself.
Yeah, to get caching back, engineering teams have to manually rebuild complex, bespoke caching logic on the server side, resolver caches, and heavy state management caches inside their client applications on the phone. It is a massive trade-off. You gain ultimate query flexibility and bandwidth efficiency, but you lose the free, globally distributed caching infrastructure of the web.
Let's pivot to a different environment, internal services. Server to server, deep inside a corporate data center. Amazon's recommendation engine talking to Amazon's inventory database. They aren't using REST or GraphQL over the public internet. They use gRPC.
Right. Inside a service mesh, where microsecond latency is critical, bandwidth is virtually unlimited, and you control both ends of the connection, you use gRPC. gRPC explicitly abandons the text-based nature of JSON. It uses binary schemas, specifically protocol buffers or protobufs.
Explain how a protocol buffer is different from just sending JSON data.
In JSON, if you want to send a user's name, you send the text string name, John. You are sending the field name, the quotes, the colon, the brackets every single time. It's structural fat. In a protocol buffer, the client and server agree on a numbered schema beforehand. They agree that field number 1 is a string representing the name. So over the wire, it just sends a tiny binary tag indicating field 1, followed immediately by the bytes for John.
Wow, that's tiny.
It strips away all the self-describing overhead, is blisteringly fast, it uses HTTP2 multiplexing natively, and it enforces strict data contracts.
So why don't we use gRPC for everything? Why doesn't my web browser talk to my bank using gRPC?
Because web browsers lack the low-level API access required to manually control the raw HTTP2 frames, which gRPC requires for its complex streaming capabilities, browsers abstract that away for security reasons. Furthermore, protobufs are not human-readable, which makes debugging client-side web apps a nightmare. So the dominant industry pattern is use REST or GraphQL at the public edge where the unpredictable browser connects, and use gRPC in the private interior where servers talk to servers at light speed.
Let's hit one final API paradigm. What if the server needs to push data to the client continuously, like live sports scores, a real-time chat app, or a stock ticker? We have 2 main options that developers constantly debate: server send events, or SSE, and WebSockets.
Server sent events, or SSE, is often overlooked, but it's brilliant for most real-time use cases. It is simply a long-lived standard HTTP DET request. The client opens a connection, and instead of sending the response and closing it, the server just keeps the connection open, streaming text events down that single direction forever.
Because it's still HTTP.
Because it is standard HTTP under the hood, it keeps all the nice features we've discussed. It works flawlessly through corporate firewalls, proxies understand it, it supports automatic reconnection natively in the browser, and it leverages standard HTTP routing. If you just need a feed of notifications or a progress bar, SSE is the right tool.
But what if I need true, real-time two-way communication, like a multiplayer browser game or a collaborative Google Doc where multiple people are typing at once? That's WebSockets. But here is where I get confused. WebSockets are incredibly fast and offer real-time bidirectional communication. Why don't we just use WebSockets for everything? Why use HTTP at all if WebSockets offer a raw open tunnel?
Because exactly what you just said,
Yep.
it is a raw tunnel. When you open a WebSocket, you start with a standard HTTP GET request, but you include a header asking to upgrade the connection. If the server agrees, the HTTP protocol is entirely stripped away. You leave HTTP entirely. You are no longer speaking the language of the web.
You leave the safety of civilization.
You step out into the wilderness. You lose everything HTTP provided. There are no safe or idempotent methods. There are no status codes to tell you if a resource was found or forbidden. There's absolutely no caching. Proxies don't understand the traffic, they just blindly forward the encrypted bytes.
Oh man.
If a WebSocket connection drops, the browser does not reconnect automatically. You have to write complex retry logic yourself. If a message fails to process, you have to write the idempotency checks yourself to ensure you don't process it twice. Load balancing 1 million persistent WebSocket connections across servers is exponentially harder than load balancing stateless HTTP requests. When you use a WebSocket, you are on your own. You only pay that massive architectural price if your application absolutely demands sustained, sub-millisecond bidirectional dialogue.
That is a phenomenal way to look at it. The decision matrix for APIs is entirely about what infrastructure you are willing to abandon for a specific optimization.
That's exactly it.
As we wrap up this deep dive, let's pull all these threads together. We have journeyed from 1997 to today. The incredible takeaway here is that the stable core of HTTP semantics, the GET and POS methods, the 200 OK status codes, the headers remained absolutely identical. You can take a developer from 1997, show them a modern HTTP3 request, and they would instantly know how to read the headers and understand what the request is doing.
It's amazing longevity.
Yet underneath that stable semantic surface, the wire format, how those bytes physically move, underwent two massive, painful, and frankly brilliant revolutions. We moved from plain text over single TCP connections to multiplexed binary frames over single TCP connections to multiplexed binary streams over UDP with QUIC. And all of it, every ounce of that immense engineering effort, was just an attempt to fight the latency of the network, to hide the speed of light from the user.
It is a profound triumph of layered system architecture. The application developers building websites never had to change their business logic to take advantage of HTTP2 or HTTP3. They just wrote their code, and the underlying network infrastructure essentially swapped out the engine while the car was driving down the highway at 100 miles an hour.
I want to leave you with a final provocative thought to chew on next time you browse the web. It's a philosophical engineering concept we can call the conservation of complexity. We spent 3 decades and billions of dollars moving the bottlenecks out of the application in HTTP 1171, pushing them down to the transport layer with HTTP2, and finally creating a bespoke supertransport with QUIC in HTTP3. We fought the physical network, and for all intents and purposes, we won. The network is no longer the slowest part of the web experience.
And that is the ultimate irony of system design. By curing the network bottleneck, we simply shifted the complexity elsewhere. Today, if you tap a link on your phone and the page feels sluggish, it's rarely the transfer time over the airwaves. The new bottleneck is the server's backend database struggling to gather the dynamic data, or worse, the massive multi-megabyte bundle of JavaScript that has to be downloaded, parsed, compiled, and rendered by the CPU of your actual mobile phone. We perfected the delivery mechanism, only to realize the device itself and the bloat of modern software is the next frontier. The complexity just conserved itself and moved to the edges.
We cured the network, and now we have to cure the phone. Thank you so much for joining us on this deep dive into the hidden nervous system of the web. Next time you tap a link, take a millisecond to appreciate the war being fought in the background to bring you that page. Keep questioning how the invisible things around you actually work, and we'll see you on the next one.